Hello learner, welcome to the learning of computer networks and security. Let's continue with the module 3 concepts. Let's continue with the network layer concepts. We'll be dealing with the distant vector algorithms and then hierarchical routing concept, and then we'll deal with the routing in internet, that is the three protocols we will discuss in detail. One is RIP, then OSPF, and then BGP. And then finally we'll conclude with the broadcasting and multicast routing techniques. Let's start with the distant vector algorithm. Alternate name for distant vector algorithm is Bellman-Ford algorithm, and I hope you all have implemented this Bellman-Ford algorithm in the lab. So the purpose of this algorithm is calculation of shortest path from source to destination. So here we need to calculate two factors. One is, the name itself indicates, D, it's nothing but distant vector that you have to estimate, and here we have taken the two variables, or you can call them as nodes, node X and node Y. So let us take node X as source and node Y as destination. So all that you have to calculate here is distant vector, or the shortest path from the source X to the destination node Y. So here the source node X maintains the distance vector that is from itself to the destination node Y, wherein we indicate n as the total number of nodes or the total number of vertices in the graph, or you can also call it as n as the number of nodes in the network. So Y is one of the node that should be belonging to this list of nodes belonging to the network. So here we have all the nodes in the network. We can call them as routers, and as you all know, every router maintains routing table. So what is the information maintained in the routing table at every node? It is nothing but the least cost path. So it is the least cost path from itself to the destination. So here node X should know two important factors. One is the cost, that is the distance. You can also call it as distance, or we can use the term called cost. So here the cost to reach from node X to each of its neighboring node, wherein the neighboring node we denote it as V. So the cost here is represented this way. This is the first factor that the router or the node X should maintain in its table. And the second information that the node X or the source node X has to maintain is its neighbor's distance vector. So here if V is the neighboring node of the source node X, then for each such neighbor, we need to calculate something called as distant vector. So this distant vector is calculated for every neighboring node, from every neighboring node to the destination node Y. So here the neighboring node, any neighboring node of source node X should have calculated already the distant vector from itself to the destination node Y. So here this distant vector calculated by the neighboring node V will be shared with the neighbor of this V. So who is the neighbor here? It is the source node X. So node V is a neighbor of source node X. So that distant vector calculated by all the neighboring nodes of source node X will be shared with this source node. So here node X should maintain two information in its table. One is the cost to reach from the source node to the neighboring node, and again the next information is the distant vector that is calculated from the neighboring node to the destination node Y. Let's see the distant vector algorithm now. So the purpose of this algorithm is calculation of shortest path. The idea behind this algorithm is every instant of time, each node in the network should send its own distant vector calculated to every neighbors of itself. So it is something like, if I have a graph, if I have a network something like this, I have say node A, and then I have for node A 2 neighbors. Let me take as B and the next node as C. So here let me take the source node as A. So let me take this, call this source node X, and here I have the destination node Z, and I have one more node that is Y. So here let me fix this source node as X and let me take this destination node as Z. So here I said already two factors has to be calculated by the source node. One is the cost to reach from the source node to each of its neighbor. So here I have two neighboring nodes for node X. One is the node B and the other is node C, or you can also call them as Y and Z. So these are the two nodes for which the cost should be known. So what is the meaning of cost? Cost is nothing but the weight of the graph. So here you can also call it as distance. Let me take the cost as 2 and this cost is 1. So the cost to reach from the source node X, that's for your understanding, source node X, to the destination node or to one of its neighboring node, is the cost is how much? It is equal to 2. Similarly, one more cost, that is the cost to reach from the source node X to the neighbor. So one of the neighbor of X, node X is Y. So what is the cost given there? It is given as 1. So these are the two costs which should be known to source node X. And one more information that is maintained is the distant vector shared by the node Z, which is the neighbor of source node X, and then the distance vector shared by the node Y, which is one more neighbor of source node X. So how is the distant vector calculated there? So distant vector is calculated something like, by using the Bellman-Ford formula. So Bellman-Ford equation you can say. So here, in order to calculate this distant vector, we need two factors. So let us see here, what is it? So when source node X receives the distant vector estimate from its neighbor, it updates its own distant vector using the following equation. So the meaning is, any node to calculate its distant vector should make use of this Bellman-Ford equation. So Bellman-Ford equation has this entire part. The first part is the cost to reach from source node X to one of the neighbor plus the distant vector that is shared from the neighboring node V to the destination node Y. So when you add those two values, you get the answer there, and that distance actually you are supposed to compare with the already calculated distant vector from the source node X to Y. So if the distance that you get finally is the minimum distance, so after you calculate this, suppose if you get the least distance, then that least distance you are going to update in the table of source node X, and you call that as the distant vector that is calculated, or the least cost path that is calculated from source node X to destination node Y. So this is the formula. So the first part is cost to reach from the source node to one of its neighbor plus the distant vector that this neighboring node has shared from this neighboring node has shared with the source node x. And what is that distant vector? It is the distance to reach from the neighboring node v to the destination node y. So when you add those two, so here in my example, if I have to calculate the distant vector, that is the distant vector to reach from the source node x to the destination node y, in that case let me take the formula as minimum of, so I have to calculate the minimum. So minimum of what? The cost to reach from x to the neighboring node. So what is the neighboring node between x and y? I have two paths. One is direct path from x to y, and there is one more path, that is to reach from x to y. So what is that direct one more path? It is via z. Via z I can also reach y. So x to z I need to know the cost, plus z to y also, that distance I need to know. So when I add those two, I get to know the distant vector, or I need to know, I'll get to know what? The distance to reach from x to y. So let me take this particular distance in my example as 3. So the distance from z to y is 3. So distance from x to z is 2, and distance from x to y is 1. So here if I'm calculating using the Bellman-Ford equation, so the first part is what? The cost to reach from x to v. So the cost to reach from x to z I need to know. So what is that cost? I have already calculated, it is 2. So the cost to reach from x to z is nothing but 2. Next, the distant vector that node z has calculated. What is it? The distance to reach from z to y. So that distance is how much? 3. So who has calculated that? The neighboring node z has calculated that, and that information is shared with the node x. So here 2 and then plus, you should add that cost 2 with the distant vector from node z to y. So the distance, how much is that? You get the answer there as 5. So what is that 5 you have to compare with? You need to compare this particular distance with the already pre-calculated distance to reach from x to y. So what is the pre-calculated distance, or you can also call it as the distant vector that is already calculated to reach from x to y? So that is nothing but I have already that distance mentioned here. So the distance to reach from x to y is 1. So here that is the pre-calculated distance 1. So now we are supposed to compare this newly calculated distance 5 with the pre-calculated distance 1. So now what is the minimum value out of these two? The minimum distance out of these two is 1. So here the final distant vector that we have found is, when you compare 1 with the 5, the minimum value is 1. So the final least cost distance to reach from the source node x to destination node y is 1 itself, which is the least value compared to all the other path. So this is how you calculate the least cost path from the source node to the destination node. So we have the algorithm here, distant vector algorithm, and here we call this particular algorithm as asynchronous algorithm. Why? Because here in the network you might have observed, so here in the network we calculate the distant vector from the source node to the destination node, and for doing this calculation, for calculating this, we need not the source node need not be synchronized with the other nodes in the network. So here synchronization is not required between the source node and the other nodes. All that the source node has to sync here is with only its neighbors. Only with its neighbors. Why? Because its neighbors has to share its distant vector with the source node. So here only that synchronization is required among the neighboring nodes and source node, but otherwise the source node need not be synchronized with the other nodes in the network. So you call this as iterative and asynchronous algorithm. So what is the meaning of iterative here, asynchronous is fine, but what is iterative? So here you can see every now and then the distant vector may change. So it is something like at time t is equal to 0, that is the first instant of time, you first calculate the least cost distance. So we are not done with the least cost calculation at the end of time t0. So we should go with the least cost calculation at the next instant of time, so wherein the neighbors would have shared the new least cost distance calculated among with the source. Okay, so this distant vector may change here at time t1. So at time t2 again you may refine your distant vector calculation and see whether it has changed. So this continues until no new information is shared. So at every instant of time actually new least cost path will be calculated, but when this algorithm iteration stops, it is when no new least cost path is calculated. So you call this distant vector algorithm as iterative and asynchronous. So we can also call this as a distributed algorithm. Why? Because here a source node, after calculating its distant vector, it will share that distant vector with its neighbors, or another way around if you are speaking, our neighbors also shares their distant vector, neighbor also shares their distant vector with the source node. So you call this as basically a distributed algorithm. So we have here recomputation happening, every now and then recomputation happening, and this continues. So you can just see here our example of calculating least cost path using distant vector algorithm. So I have a simple network wherein I have 3 nodes. So first node is x, and then the second node is y, and the last node is z, and the cost to reach from x to y is 2, y to z is 1, and then x to z the cost is 7. So I have here in my example initially in the first iteration, so let me call this as iteration 1. So wherein I have in my iteration 1 I have here the node x, and then the node y, and then finally the node z. Total 3 nodes I have. So all 3 nodes have initialized their values here. So here in the iteration 1 I can see the initialization happening, and the initialization is actually the distance from a source node to itself is taken as 0, or distance from every node to itself is always taken as 0. That is one initialization, and one more is a distance from a node to a faraway node. So you can also call it as distance from a node to a non-neighboring node is taken as infinity. It is considered as infinity. So a node to a non-neighboring node, you distance you initialize it to infinity. So you can see the initialization of node x in the iteration 1. So what is the initial value of node x? So initial value of node x, we have written that in the form of a matrix where every row indicates the source node, whereas every column here in the matrix indicates the destination node. So here source to destination we calculate the distance, and that is entered inside here within the matrix. And what is the initial value of node x? Source node x to the destination, to all the other nodes y, x, y and z. So we can see here the distance from node x to x is anyway 0. And what is the distance, initial distance from x to y? So initial distance from x to y is taken as the cost to reach from the source node x to y. So that cost is taken as 2. The cost is taken as 2, and you can find here the cost is 2. Next, source node x to z, the source node x to z, the cost is how much? It is equal to 7. So here just for your understanding purpose, here you can note that no nodes have even shared their information till now. So it is all about the node x which has calculated the cost to reach from itself to to reach from the source node, that is itself, to its neighbors. So here the cost to reach from x to z is 7. Okay, so here next we have all the other values, it is set to infinity. The other values we have set to infinity. So here y to x, y to y, and y to z. So all the others you can call it as something like we have these as non-source nodes. So this is the only source node that we are speaking about here. Next we have node y, wherein the initial values set for node y, that is the cost to reach from y to x, then y to z, it is 2, and then y to y itself is 0, and then y to z the cost is equal to 1. So here that distance is updated because this is the initial value. Rest all the other values are set to infinity. Why? Because we are initializing only the source node y. Next we have the source node z, wherein all the initial values I take it as z to x is 7, z to y is 1, and then finally z to z is taken as 0. Rest all the other values are set to infinity. The meaning is, again here we are initializing the source node z values. So what do we do in the next iteration? So iteration 2, this continues. Now as our Bellman-Ford algorithm says, every node should share its information with its neighbors. So here every node has to share its information with its neighbors. So here first node x will share its information with its neighbors. So who are the neighbors of node x? It's node y and node z. So node y and node z we have. So we can see here node x is having an arrow mark. So you can just see here. Yes, about this we will see later. What node x is sharing? Node x is sharing with actually node y and node z. So about that we'll see here next. But here in the iteration 2 we'll see first how node x will refine its least cost distance, or how node x will update its matrix. In order to update the distance value here for node x, it has to obtain the information, or it has to obtain the distant vector what node y has calculated and what node z has calculated. Because for node x, who are the neighbors? For node x, the neighbors are node y and node z. So both node y and node z has to share their distant vector with the node x. So here node y is sharing as well as node z is sharing, and we can just see here what node y has shared. What node y has shared is 2, 0, 1, and what node z has shared here is 7, 1 and 0. So here these are the two rows which are shared by node y and z, and with the help of these information, with the help of this distance information, our node x will update its distant vector. Now we'll see how node x will update its distant vector with the help of our Bellman-Ford formula. So anyways, we know that from node x to x the distance is 0, it can never change. But how to calculate the distance from node x to node y with the help of the information shared by the neighbors? So here we'll make use of our Bellman-Ford equation, and you all can see this equation, minimum of cost from x to y. So if first I'll calculate the distance from x to y. So how do I calculate from x to y? First I need to know the cost to reach from x to y, which I need to add with the distant vector that is shared by y. So which is the distant vector shared by y? So it is this, the distant vector shared by y with x. So that distant vector I need to calculate, and then I need to add that, and then one more factor that I have to find out is the z, about the distance from x to z. So here the distance from the cost to reach from x to z, I can see here the cost to reach from x to z, which I need to add with the distant vector that our z has shared with x. So what is the distance vector that our z has shared with x? That is 7. So I need to add those two values and compare. So we'll just see here. So x to y. So what is the distance to reach? So you can just see here in the graph again. So here from x I am calculating. First I'll see the distance, shortest distance from x to y. So one is direct, that is 2, cost is 2. So cost is 2, you can just see here in the equation. If you want, just I'll just see right here. So the distance to reach from x to y, the cost to reach from x to y is 2, which I need to add with the distant vector shared by y with x. So what is that? The distance to reach from, you can say here, here one point has to be noted. I am calculating the distance from x to y. So here x to y I am calculating. So the destination here for me is y itself. So x is a source wherein y is a destination. So when I am calculating the distant vector from source node x to destination node y, the cost to reach from x to y I have to take it as 2, whereas the distant vector that I am calculating now is from y to y. So here y has to share its distant vector. So the distance vector that is from y to y is taken as always 0, because y to y is node from itself, right? So that I need to compare now with the next part. So what is that? I have one more path to reach from x to y, that is x to z, and then via z, that is z to y. So what is the cost to reach from x to z? Since z is a neighbor of x, we know this cost, right? So what is that cost? That cost x to z is taken as 7, and then there is one more cost or one more distant vector what z is calculating. That distant vector is taken as from z to y, distance to reach from z to y, and that I have taken it as 1. So here cost to reach from x to z is 7, whereas the distant vector that is taken from z to y is 1. So 7 plus 1. Now out of these two values we need to consider the least value, that is the minimum value. So what is the answer here? 2, and then here 7 plus 1 is 8. So minimum of these two, what we get here is finally 2. So this is how I calculate the minimum distance minimum distance from x to the destination node y. So here I need to get the answer, that is x to y, the shortest distance is actually equal to 2. So do we know that? Yes. Are we getting that? Yes. So next we have the cost to reach from x to z. So the distance to reach from x to z. So how do I calculate? X to z is equal to 1 is the cost, z is a destination now, and x is a source now. So x to z, the distance is 7, and then you need to add that with the distant vector of z, that is z to z itself, which I have to take it as 0. So 7 plus 0 is actually 7. So you can also calculate over here and keep it ready. So the cost to reach from x to z is 7, which you need to add with the distance from z to itself, which is actually equal to 0. Next, that is this is the direct path I have, and there is one more path via y. So x can reach z via y. So here the cost to reach from x to y is 2, and then the distant vector from x to z, or the distant vector what y has calculated, it is 1. So from y to z is 1. So 2 plus 1, that is 3. So I have to now take the minimum value out of these two. So what is the minimum value out of these two? The minimum value is equal to 3. So now I have already obtained the information, this information from z. Z has already informed me that, informed the source that 7 is the cost to reach from z to x, and also z has informed that, z has informed x that the distant vector from or the distance from z to y is equal to 1. So with the help of these two information, our x could calculate the shortest distance to reach from x to z, that is equal to 3. So 0, 2, 3. So now this 3, when you are writing, you have to compare with the previously stored value. Already I had taken the distance from x to z as 7. So you need to compare this distance with the newly calculated distance. So whether this newly calculated distance is minimum compared to previous? Yes, it is minimum. So 3 is less than 7. That is why we have to consider now 3. 7 has to be replaced by 3. So can we see that 3 is the minimum distance? So anyways, here it is calculated that minimum distance, and here that is how we calculate the minimum distance. Okay. I hope you can now calculate all the other distances as well. So till now we have just calculated this source node y, from source node y to the other destination nodes y and z. Now in the same iteration you can also see the next source node I have. And what is that next source node? Next we are changing the source node now, so next source node is y, wherein that has to calculate the distance, least cost distance, with the help of the distance shared by x and z. So our neighbors, two neighbors we have for source node y, one is x and the other one is z. And you can just see with the help of these two information. So how did I get these two information? 0, 2, 7 and 7, 1, 0. So we got this information from the previous iteration. So node x has shared its distance vector here with node y. Again node z also has shared its distance vector with the node y. So here these two information shared is written over here directly, 0, 2, 7 and 7, 1, 0. But this 2, 0, 1 is the one which we have calculated right now in this iteration with the help of Bellman-Ford equation. So Bellman-Ford equation, with the help of that you calculate this. Similarly the next node, the last node, that is the source node z we have, and wherein I'm taking here the information node shared by our node x and node y. Why? Because for z we have two neighbors x and y. With the help of these two information which we got from the previous iteration, we calculate the shortest path. And the shortest path, when we are calculating, we use the Bellman-Ford equation, and again we need to compare with the previously calculated values. So here I have 7 which was pre-calculated. Now the newly calculated distance is 3, that is from z to x. You compare here 3 whether it is less than 7. Yes, if it is less than 7, just replace that 7 by 3. So whereas 1, it is same to same, previously also I got this one, and 0 is anyway same. So this now, or in this iteration, whatever the 3 nodes have calculated, its distance value is shared with the neighbors in the next iteration. Now when you go for the iteration 3, the last iteration, you can see here the iteration 3, again when node x is trying to calculate its shortest distance, who has to help? Its neighbors. So that is y and z has to share their shortest distance. So you can just see here how they have shared. 201 was already calculated in previous iteration, 310 is again calculated in the previous iteration. So those two rows are directly added over here. With the help of those two, we are calculating the shortest distance 0 to 3. So this is the one updated, and you can just find out, compare that with the previously calculated distance. It is same to same, no changes, so keep it as it is. Next I have again y is updating. So 201 is the distance that it is getting with the help of x and y z information. Yes, so here we have with that no changes with the compared to previous value. And finally we have 310, again here also we have no changes. So we don't have to go for the further iteration with this. So with this I guess we can stop with the iteration, and this is how the Bellman-Ford algorithm works.